Hey class, so I've posted exam 3. It'll be due next Tuesday. Um, so it's the last of your coursework. We will have a lecture today and Thursday, and then we'll leave you be to complete the rest of your finals. Okay, I wanted to share a final thought on the zeta function. Well, final enough for now. And then I wanted to uh, just briefly show you what's on the exam, walk you through it. I understand you probably already have this. These are very similar questions to what you faced on the homeworks in previous exams. And then I was thinking about reviewing the material from the semester, but I feel like the exam kind of does that for us, and we already have all of the lectures. And so I thought it would be um, I thought it would be more interesting to try and work through um, a problem where maybe you're dumped in and you don't know a whole lot. So sort of talking through a more complicated problem and just finding rhythm in terms of working through um, gaps in understanding and approaches that you can take to try and create these footholds uh, and sort of chip away at a problem. Okay, so so the zeta function. Right? Okay, so this is the inverse here, so it's 1 over 1 minus this or whatever. And again, these are the generators of the geometric series, right? All of the geometric series. And so last time, I presented an argument that this should really be extended into the critical region. And one of the things that, the reason that it isn't in general, I guess, is because it's said to diverge for those values in there. But it's interesting that it doesn't necessarily. And when it doesn't, when it goes to 0, then it obviously converges, and it converges to 0, right? Um, so these values, if we accept that that's applicable, one of the things that you'll see if you get enough primes is that you can. So we have this thing which uses this infinite product of all of these values, which are individually conceived to be non-zero, but they relate so intimately to this these geometric series and the summation that results from their product that it can still go to 0, even though none of them are themselves 0. And so I think that's really interesting. But what's additionally interesting is that so we've defined it in terms of these, and not like a polynomial where you have this function x minus 2 equals 0, or times x minus 5 equals 0, and you can add however many of these you want. You get this polynomial that equals 0, right? So right, and so we don't have that over here. We haven't used is it the Hadamard definition of it? Maybe the Weierstrass definition of it, where we define it in terms of zeros. Here we've defined it just in terms of of the prime numbers and the geometric series that it represents. Right? So, this is the first expression I've seen of a function defined like this, right? Like you see them, with integrals and stuff like that as well. But like something that so closely should be a polynomial yet is not. Without removing the zeros, you can remove however many of these you want. So, okay, so there's this minus 1 over here. Let's write it out to be explicit, I guess. So So this was a reciprocal. So it's 1 over this expression, right? But we can remove however many terms of them we want, so long as it's a finite number. So okay. So we remove the first 4 terms, all of the prime numbers that are less than 10, and so now we have this smaller product series, right, where we begin after the prime number 7, so all of the primes larger than 7. And what I find remarkable is that we haven't changed any of the non-trivial points s where this product is 0. And it makes sense, right? Each one of these is really just a constant, so you pick some value s, and these are all going to be non-zero values. So we're multiplying by these non-zero values. They resolve into a constant. So you would expect that anywhere that this was 0 before, it's still 0. But I guess it just didn't click to me when I first saw it, because we've defined it in terms of the primes. And so it's fascinating to me that we've used only the prime numbers to define these, and then we can remove however many we want, so long as it's finitely many, without changing the very nature of the function it's defining. It doesn't change those non-trivial zeros at all. And so there's this question of the generalized Riemann hypothesis and the what was it called? The Dirichlet character function, the whatever. And so there's all of these alternative definitions where you're removing these primes, and then whenever you put in this notation, and particularly this notation, you see that all of the ones where you remove just a single prime number, or where you remove all of the factors of a given number, right? All of the prime factors, then all of those character functions, whenever they're fed into the zeta function, they will have, because of this, they will have all of the same non-trivial zeros as the zeta function. So those inherit the property that they all lie on the critical line as well. And there's other ways to consider the problem. But I just like this, right? So that essentially this function, it looks like it's defined in terms of the prime numbers, but the zeros, the points that essentially give the character to the function, are defined by all of the prime numbers that we do not explicitly state, right? So there's always this infinite collection of prime numbers. There's always infinitely many more. And as long as we only remove finitely many, then this function, it continues to be defined by this mysterious unknown set of prime numbers, and I really like that. And so you say, okay, well, maybe you didn't say, right? But so I'm saying, right, that the nature of the function, the zeros really start moving around once you remove countably many. So if you remove all of the prime numbers, which leave a remainder of 3 whenever you divide by 4, or which leave a remainder of 5 when you divide by 6. Things of that nature, right? Where you start using this modulus operator to select which prime numbers you want instead of removing finitely many. When you start using rules to remove countably many, then those zeros start to slide up and down the critical line, and you could demonstrate it for a few that's the case. But what starts to get difficult is whenever you start making arbitrary selections of that, right? So you remove all of the ones that are leave a remainder of 5, or the ones that leave a remainder of 7 whenever you you take the modulus of 12, you have to demonstrate essentially that there are infinitely many primes remaining along um, the arithmetic progressions that you choose to keep, right? And so then each one of them is going to define not the zeta function, right, because the zeta is defined by this, but by something that's zeta adjacent, or some cousin of the zeta function, if you want to think of it that way. But the trick there is to show that that these classes of arithmetic progressions all possess infinitely many primes, and if it might have already been demonstrated, I don't know. In which case, maybe the result would follow for the general case, but it wasn't something that I was aware of, and so I just was satisfied with finding this really cool result that you can define it strictly in terms of this, and then remove however many you want, and it essentially doesn't change the nature of the function. Okay, I thought that was really cool. Okay, so let's take a look over the exam, and then we will begin our conjecturing. Okay. Alright, so the first question is going to go back to homogeneous recurrence relations. So these are second order problems, right? Have a solution like this, as you recall from the notes. This is how you solve for the constants using the initial conditions, and then you just produce a solution to second order problems. Okay, this one goes back to the product rule, and so you're choosing an R permutation, right? So look up the rules for that. It should be fairly straightforward. This one again, it's a slightly trickier version of the R permutation, but I'm certain that if you think about it for a little bit, you will be able to come up with the solution. Okay, relations. Yeah, you have to select the result set from this table, given this query, right? And so you list the result set, the tuples that satisfy the selection criterion. Okay? And then again, same thing here. Okay, so in the graph, you fill in the appropriate values for the adjacency matrix, right, for the weighted graph. And then trees, subtrees, pretty simple. And then implement the sieve of Eratosthenes, and then you can choose which language you want, but whenever you upload it, I want you to name it appropriately and include the appropriate file name or extension type for the file, to give a hint as to what programming language it is, if you don't leave it in the comments or whatever. But it should be obvious, I would hope, whenever you submit it, what language you use to program it in. Okay, so that's the exam. Okay, so okay, so whenever we look at our world in our three-dimensional world, we tend to look at it in terms of the two-dimensional surface on it. So you get a map. It's a grid, right? It's just x and y coordinates, and the map may make efforts to give some awareness to altitude. But you have to sort of derive those results. You have to think about it. You have to interpret the map. But the intuition is really all housed inside of uh, the x and the y, right? Just those two dimensions. And so we approximate our three-dimensional world with a two-dimensional surface. And we do so using charts, right? These charts and then bundles of charts. Yeah, the MapQuest I forget the it might have been MapQuest, but the maps that you used to get, right? The atlas or that bundles together all of these individual charts. So. Okay, so so if this is the part of the world that you live in, then you would have this map that approximates it. And the further out you get from wherever it was taken, that's this thinner, right, where it was surveyed. The air is going to increase as you get towards the edges. So really, what you would want to do is kind of have these overlapping areas. You could kind of stitch it together. You could make this like patchwork quilt type of covering for the Earth, really. Right, so something like that. And then eventually, if you had enough of them, you could fully represent this over here with your patchwork quilt of maps. We'll call it an atlas. And so this is your approximation for what's actually happening. But this is what you have to work with, right? We print things in two dimensions. I guess we do have 3D printers now, right? But in terms of reading a map, we're going to approximate it using 2 dimensions. And it makes sense, right? Because we have a 3-dimensional object. And so as a rule, you tend to go down 1 dimension whenever you're approximating it. And then if you have enough of those approximations, you can stitch back together the picture of what was happening at the higher level. And so this idea, this quilt, it is called, a covering, right? So we can pick all of these smaller regions to study on this global object, and if we have one of these, right? If for any point on this it's at least represented by one of these, then we say that we have a covering of the space. We've got it covered, right? So we'll just write that down, right? So a covering. And now all of the questions that we ask in terms of how things relate to each other, how you get from one city to the next, we don't look at the globe anymore. Now we look at the local maps, and you can add whatever additional information you want in those contexts, right? So number of jobs added in a particular region and so forth, right? But we do all of our study here, and whether those concepts can be applied globally, we look at them locally with the awareness that it's part of a bigger picture. That it is just one bundle within the overall atlas. Right? Okay, so that idea of splitting things up into a covering that exists, with just the real number line. And so you can have it to where there's a little bit of buffer on either side of the integers, right? So that you're always covering one plus epsilon or epsilon over 2 on either side, right? So you always have a little bit more, and you always get it. And then there's overlap. Right? And so on and so forth. So at this interval, as represented by this this set, right, this open set, overlaps with this one, and so you have this non-zero intersection. And you can continue to make the overlap as small as you want, right? Like you can push these to the edges. But if you ever make it so that it's entirely, so you can make it as small, if you're using closed intervals, right, where you include the endpoints, then you're only overlapping by countably many points, right? And this is acceptable. There's a good deal of arithmetic that those of you that take real analysis will spend time studying, basically to say, yeah, it's fine. You can throw out however many points you want. You can throw out an infinitely many number of points, so long as it's only countably infinite, right? So all of the integers, positive, negative, and 0, make up less. They are smaller in measure than however small you made this overlap, right? Anything larger than 0, right, from here to here, is going to be, it's going to add to the total measure. You're going to be recounting some values or some behaviors or whatever. And so it's difficult to make statements in terms of like one-to-one relationships because you've double counted some values. And so the ability to feed your information forward and process it is going to be hindered if you don't do it. And so the recommended path is, if you can, choose a disjoint covering of sets. So the idea is that we have the open intervals. We push these essentially, and we miss infinitely many points. But those points, those infinitely many points that we miss, have measure 0, right? So it's kind of okay. Essentially, we're only missing the edges. And whenever you print something out, every the edge, each point has larger than 0 width or whatever. We count the density in terms of dots per inch or square inch, and so each dot has some amount of width. But the points on the number line do not. So even if we throw out infinitely many, so long as it's countably infinite, then we're not missing a whole lot. And so it's fair to ask whether or not it's still a covering if you're throwing away infinitely many points. I forget what the resolution to it is, but the gist of it is, you get to choose, right? That okay, I think I remember what the trick was. Right? So now we shrink these down. And so on and so forth. So we use these closed intervals, right? And this is just the real number line, right? So we'll come back to 2, 3, and 4 dimensions in a little bit, right? So we use the closed interval, and the point 1 overlaps between this interval 0 to 1, where we include the endpoints, and 1 to 2. But the size of the overlap is a measure 0. So the way that we would put it, right? If we label this set A and the second one B, then then the intersection of A and B is just a single point. It's the point 1. And then the Lebesgue measure, which will come up later, in the context of the number line, it's essentially, I guess it's more than a distance function. It's the area function, right? But if we were to measure this set, right, like all of the, I mean, if we were to measure the span of this set, how much room is the set actually taking up, then we would see that the measure of this intersection, the measure of just a single point, is 0. And so now, in using these closed intervals, we have a nearly disjoint collection of sets which cover the real number line and whose intersection has measure 0. And so if we need to make statements against open intervals or open coverings, then we use the interiors of these sets. So same size set, you just drop the endpoints, and then it allows you to make these statements about these open coverings, right? And so this is just essentially stitching one place to the next. And so the same concept of having them just share the borders and then using the interior whenever it's appropriate to speak of open sets, and then using the whole thing whenever you need to make statements about covering, right? About making sure that you have every region of space, the space under consideration, covered by one of your maps, by one of your local statements about what's going on. And so this carries up. We can promote this to the second level, because the region that they overlap, it's just small enough. It's the perfect amount. It's a width 0, and so it kind of gives us what we need. So then, if we were to apply that here, then there's a few different ways that we could do it. So one is to just correct this. So you start with some covering, and then you go back and you remove the parts that were counted twice. So this map now gets updated to have like a panhandle, basically. And then the same thing over here. Okay, and so now it's disjoint except at the boundary, right? And you could go through and you could cover everything else. If we called this all one patch, then we could be done, right? The complement to this region would be the rest of it. But it would be nice to have a covering, right? Something other than just have the complement, right? Have it all included in the interior of some other object that we're keeping track of. So I wouldn't call that a proper covering if you just left the rest of it like that. Okay, so that's one way. Another way would be to try to do it with circles. I'm not sure how successful it's going to be on the surface of a sphere, right? But and so you would end up, with something like these circles, and then you would end up with these regions in between. And so you could count those as well, and those would those would carry over, and there would be circles over there or whatever, and so you'd have this collection of these circular regions. And that's just another guess, and that would get you, close enough. But this one, you would almost certainly have lots of overlaps. Then you would go back and correct to decide which map was authoritative over which regions and so forth. And so, computationally, whenever you divide this up, whenever you break the region that you're evaluating up, you're going to have to make these choices so you don't double count the regions. But another way to do it, something that is the topographical approach, right? So you define a global sea level, which moves based on the tide or whatever. But if you could assume that you had something that you could define as zero altitude as some baseline, then you could get a map of the surface of the Earth, and you could break it up into regions which are below the sea level and into regions which are above the sea level, right? And so anywhere that is exactly altitude 0 now becomes your boundary point. Okay, so now, so the continents, right? Everything that's above ground. So they would be above ground, with the exception of regions like Death Valley, right? Where you'd have these little isolated pockets, which are actually inland, right? They're within the coast, but they are below sea level. So you would cut those out whenever you performed this mapping. And so everything that's above would be, inside of this one map, which is above sea level, and then you would remove all of the isolated points, or they're not isolated points, right? They're all regions. They all have some area that they take up, which are below sea level, and you would put those in the complementary map. So above sea level, so then you end up over here with charts, which are essentially the ocean floors, and then those regions which were removed from above sea level. So this would be below sea level. And then once you've broken the regions up, like once you've covered your original surface, then you could break it up however you want. You could just start slicing it up over here. So that everything gets its own chart, and then this one would get its own chart, and then it's just a little more manageable. And so you would keep it in two books: above ground or above sea level and below sea level. Okay, and so that's maybe not the first thing that you would go to, because whenever you're trying to cover it, you're probably thinking of the number line and trying to keep things consecutive. But maybe there's something interesting to be said whenever you go up versus whenever you go down, and it's worth it to keep those charts. For instance, if you were breaking it up by the type of life that you would encounter, so the Indo-Rheic areas of these continents, the ones that are below sea level but are completely dried out, those tend to be deserts. So it was a place where there was a body of water, and then it got cut off from the sea, and then it dried up over time, and now it's extremely dry, and nothing is living there. So it wouldn't make significant contributions to the type of life that it's hosting, but it could live in this below sea level portion, and then everything else would make sense to study there, and then all of the air breathing life, the ones that live in the surface, would have their own sort of story to tell. Right? Okay. So we've discussed the concept of coverings, right? So you have this thing that is either finite or infinite, and then you split it up, and you just make sure that every region is covered so you can make statements against the whole thing. But it's a little easier to discuss the case where it's finite rather than infinite, because computers do better with finite objects than they do with infinite objects, especially when you ask them to count the whole thing. Okay. So let's let's step it up and go into 4 dimensions. So here we have a 3-dimensional object with 2-dimensional surface area. So then, what is it like to discuss something that is has is a 4-dimensional object with a 3-dimensional surface area? Well, it's not so different from a sphere. So. So I want to talk about this in the context of waves. Right? So let's go back and we'll consider the 1-dimensional object, a string, for example, and how a wave behaves with it. Right? So a string tied to 2 posts or whatever will sit still, and then you introduce energy. And now you have this action through this new dimension, right? So before you had the x dimension, and now you have the y dimension to describe the wave. So the displacement from the mean is going to be f of x, and this function will describe the displacement at a particular point along the line. And then now, if you think about it in terms of 2 dimensions, if you have this still pond, then it's just there, it's placid, it's not doing anything. That came out looking more like a pie than a pond with waves on it, but that was the spirit of what I was going for, was the wave. So now you have this area, this region, which now has this altitude, basically this vertical displacement up or down, troughs and crests of the wave, and so you have your field x and y, and then you have your displacement function. Which depends on both x and y, and now describes the displacement from the mean in another dimension, right? Up and down. Um, so here, the one-dimensional object, you add energy. You need a second dimension to describe it. Here, two-dimensional object, you add energy. You need a third dimension to describe it. So if you have a three-dimensional region and you add energy, then you need a fourth dimension to describe it, something to describe the wavy nature of it. And so so drawing that is a little bit more complicated. But let's keep in mind the abstraction, right? So you need one more dimension in the region than just the flat region of space that you're considering in order to describe a wave in that space. It needs something to wave through. Okay, so so whenever we create a closed off analog of this, like something that is a circle, right? Then then it's going to have this one-dimensional boundary. Whenever we promote this to the next dimension, we would take two circles, right? So the boundary was one dimension as before, but now we want to go from a two-dimensional object to a three-dimensional object. So this was two dimensions with a one-dimensional boundary. Right? You can go left or you can go right from any point, or clockwise and counterclockwise. And those are the only directions you can go while walking around the boundary. So we want to promote the boundary by a dimension and the overall object itself by a dimension. And so the way we do that is by making a whoopee cushion or a balloon or whatever. And so we take two copies of the circle and we stitch them together and then we inflate it. So we've stitched them together. They're laying flat on top of each other. And this is the bottom one, and this is the top one, or this is, the. If you think of a balloon, right? Like there's a top and a bottom part, and you blow air into it and it expands. So here we had basically sheets of paper which we stick together, and now we're, you think of sewing it together or whatever, right? But we're going to expand it. It might be easier to think of cloth and then stuffing the cloth with something. So you have something like a pillowcase, right? But that's not round. We're doing this in an ideal sense to get something that's perfectly round afterwards. Right? So we do that. We inflate the whoopee cushion. So what was the center of the interior over here, it becomes the South Pole once we inflate it. What was the center of the interior up here, it becomes the North Pole. And then these reference points that we put along the boundary, those become reference points along the equator. Okay, so now we have our three-dimensional object with a two-dimensional surface area, and so we want to make a four-dimensional object with a three-dimensional surface area. In order to do that, we need we're going to need two spheres. Okay, give me just a moment. Okay, so I've labeled 6 reference points on each sphere, right? So 4 points along the equators, and then 2 points at each of the poles. And then these are chiral spheres, you could think of it. So any small region of space in either one is going to be indistinguishable from any other region of space. You wouldn't be able to tell that there is this nature. Just like if you're in the plains of Texas, it looks like you can see for miles straight ahead across this flat land. There's not a lot of indication that there's this big round world. It all seems pretty flat wherever you are. There are these deviations, but they all just seem like these local perturbations. But overall, the whole thing should be flat. And so it's so similar is it in space, right? It seems like, well, okay, there's these planets and there's these deviations in terms of gravitational potential. There's these deviations in terms of electricity and so forth. But more or less, it's all flat, right? But let's consider that may not be the case. That it might, in turn, be more likely that this is actually what's going on, right? Okay, so I said these are chiral spheres. This is one object, even though it's 2 spheres. And the reason that it's one object is because there's no better way that I'm aware of to draw a 4-dimensional object, right, on a static surface. You might be able to do something a little bit more if you had time evolution, right? Because the time factor, allows you to evolve a video or something like that, so you can introduce a 4th dimension conceptually that way. But I think this is probably a better representation. So this is one object, and so to give you hints, just like whenever we zip together or we stitch together the whoopee cushion or the balloon or the pillowcase or whatever, we took 2 halves and we stitched them together to create this larger object. And so that's just something that we say conceptually. So a 4-dimensional object wouldn't necessarily have stitches on it, right? And so in order to represent it, right, we have to divide it into the chiral halves, right? A left half and a right half, or top and bottom, or north and south or whatever, or Australis and Borealis, which I really like. But because it's one object, the reference points act as a key for where it's stitched together. So, so the point Aleph, right here, on the left-handed one, is the same as Aleph on the right-handed one. So if you had a ship or a planet or whatever, and it was passing through this point, if it went in this direction, this point is exactly the same as this point, right? This is just a visualization helper, right? But these are the same points. So if it was coming in over here, then it would continue on over here, and it would carry straight across, and the great circle would pass through here, right? So you could go, hypothetically, you could go in a straight line if you had forever and another forever on top of that. In order to do it, you could go in a straight line, you could come back right to where you started, right? And then, let's see, Bet over here, it's the same thing. These two are the same point, and they're in fact the same point. Let's see, Gimel, right, over here and over here. So if you were going up, you'd carry on over here, you'd go up, carry on over here, right? Because Dalet is also the same point. Right? Carry on. Okay. And then, let's see. Het, I believe, is this one, right? Sorry, I drew it as pi, but it should have been or hey. I have to double check the pronunciation on that. And then Vav. Yeah, Vav and Vav are the same point. Right? So if you're coming over here, you pick up over here, you'd go to hey, and you'd come back over here, and you would go back to that center point. And then yeah, Zion. And then Het. Oh, so this is Vav, right? Vav. And then Zion would represent the center of Australis, and then Het would represent the center of Borealis. So the southern sphere and the northern sphere. Okay, and so you could represent now this the three-dimensional surface, right, of a four-dimensional object. And so any region in here, and you just pick any sphere to encapsulate any region, like something the size of a solar system, right? And those regions would become your coverings. So that's the geographical way to break it up. But then we could also break it up by topology, right? So the incentive that we had for doing this in the first place was that each time that we had to represent a wave, we had to add a dimension in order to have some representation of the up and down motion of the wave, or the in and out, or the positive and negative, troughs and crests of the wave. We needed an additional dimension, right? So now we've invoked this four-dimensional structure in order to have something which has three spatial dimensions, and then the displacement dimension, the one that goes in and out. And so this is just the surface area of our four-dimensional object, because everything is still 3 dimensions as you look at it, but it's just the surface area. And so it's fair to ask, what does the interior of such a thing look like? Okay, so you can approximate it. If you want, you could try to imagine this. Um, okay. So that's a circle, right? It's this two-dimensional object with this one-dimensional surface area. And if you wanted to ask what the interior looked like just by looking at the exterior, it's basically the same thing, but you start shrinking the radius in. So. Right, so that you end up getting all of these concentric circles, and if you took this continuum of them, then that would make up the object. So if we wanted to do the same thing and we wanted to represent a four-dimensional object, then we would need a series of these, right, of these four-dimensional structures, or these pair of spheres which represent the three-dimensional surface area of a four-dimensional object. We would need this continuum of them where we continue to shrink the radius, right? And so it would have an analogous representation. But right now we're really only concerned about the surface area. So then we break them up. We can break up the regions, into galaxies, and then solar systems if we want, or star systems or whatever. And then you can continue to break it all the way down, into the atomic level if you wanted. But if you're going to go, to the atomic level, or we'll call it atomic, right? Then I think it would be interesting to, at that point, return to the idea of the topographic view, right? So now you break up the regions where you have the sea level, you have this average, this mean waterline level, right? What appears to be flat space for any region, and then you have these deviations up and down, or in and out, or that perturb the surface of this three-dimensional surface. And so, it sounds bizarre until you consider that that's exactly what light is. Right? So light is a wave through three dimensions. It's this perturbation that's going through it. And so, let's see. So still, we're essentially choosing a covering. We're choosing what's most convenient. So now, we've isolated it. We're really only considering like a few atoms at a time in order to discuss the topic. And so, we're not trying to represent the universe as a whole anymore. Right? We're trying to represent just some closed region of space, whatever is inside the near vacuum that we're considering. And so it's a little bit easier if we consider it with colors, because we need something to represent in and out. We're dealing with a two-dimensional surface, and we're trying to draw in four dimensions, right? So let's use blue and green. Okay, so we have these regions of space, and that came out terribly, right? But I'll do what I can. So we have these regions where there's this concentration of aspiration or inspiration, or where there's way more troughs than there are crests, or way more crests than there are troughs. In the nautical sense, we would call it a swell, right? There's just this bulge of where there's this concentration of of the medium, right? Where it is highly concentrated, and there's this huge potential difference, um, and that is it, right? And so, in the context of of our world, I understand that to be where charge comes from. So that is exactly what charge is. So, in one direction, right, you have negative charge. So that if you have, we'll say, I can't say for certain whether uh, uh, inspiration, whenever it's displaced towards the center of the universe, right? The center of this four-dimensional structure is negative charge or positive charge, but because its displacement is negative, let's hypothesize that that is where negative charge comes from. And then there's these altitudes, this aspiration, or wherever it swells away from the center of this four-dimensional object, and we'll call that positive charge, even though we don't know necessarily that is the same thing as what we consider positive charge. But it creates these potential indifference, and so the so now we can begin to speculate. So we have this concept that that lends itself towards possibly describing something like what our universe behaves as, and so now we start to challenge it, or we start to feed into it, right? So we ask, well, what sorts of questions can a model like this answer for us? And so one of the main things that would be desirable is to come up with a unified theory for what's happening at the atomic level. And so there are competing ideas. There's Einstein's relativity, and then there's the quantum mechanics that was put forth by Planck and Schrodinger, and I'm quite certain I'm forgetting a handful of others, or many others, right? And so the idea that there are just these spontaneous behaviors that kind of come up, and I've always found the quantum model. It just feels for one, it feels a little bit out of reach, feels unnecessarily complicated, but it's just not satisfying either, right? So you go down small enough and things stop behaving the way that they are at a larger level, but that I have trouble with it. It seems like something is missing, right? That there is some deeper understanding that is missing, and the fact that it doesn't agree with relativity, which has been observed, at least in terms of like time dilation and things, and the drift of clocks from our satellites, which agrees with the time dilation proposed by oh man, can't even think of it right now. Lorentz, yes, Lorentz contraction. Anyway, so it seems to me that at some point relativity is going to have to factor in. So this model would agree with relativity in terms of the fact that the field is being updated by the waves. Or, we can construct this model. It allows for that, without any real issue, so that all of the wave mechanics, the arithmetic, superposition and interference of waves, that can be used to build up the model. And then additionally, there's at a photon level, if we include photons in this, then we can begin to consider the ramifications of displacement acting as both gravity and as charged regions. What that would mean on light, on on photons, on these packets of energy. And so if you, so now let's take a second. So we have this idea, right? So let's take a second to consider tidal forces. Okay, so the Earth and the Moon are acting on one another, but the Earth is much larger than the Moon. And so we always say that if you get far enough away from some really large object, then you can treat that object as having all of its mass located at a single point, all of it located at the center of mass. And so the center of the mass for the Earth is probably going to be really close to the geometric mean for the Earth, right? So it's going to be really close to the center of the object that we think of as the Earth, right? And the same will be true for the Moon. But then that global minimum, right? If you get far enough away from the Earth and the Moon together, like if you go out to Mars or whatever, then the system, those two objects, are going to average out to have some global minimum, and it's going to be neither of these. It's going to be the very center of the system. It's going to be the average of all of the bodies considered in the system. And so that'll be somewhere like right here, right? And so the Moon will revolve around the Earth, and this point will, and it'll go around, and it'll, I believe it has this effect of like a butter churner, right? And so I think it contributes, I don't know to the extent to which it might, but having the global minimum moving around the center of mass for this object, right? I think it, moves it creates this contraction and relaxation that is a lot like massaging the iron core of the Earth, and so I think the Moon plays a role in keeping the Earth's core active, and I'm quite sure I ripped that off from somewhere, so I doubt that's an original idea, right? But I think in my mind now I'm motivated as having this reason for it, right? This butter churner effect of the Moon. And the global minimum of the system being offset from the center of the Earth itself, right? Okay, but that's just a point, right? So the Earth as a whole is going to be pulled towards the Moon, and the Moon is pulled towards the Earth. But this side of the Earth is closer than this side of the Earth, and so it moves a disproportionate amount. So the center of mass, right, will move something like that. Right? The side that's closer to the Moon will move something further, right? Some larger amount, because it's closer, right? And the inverse squared law kicks in, right? So it's however many, it's like 100 miles closer or something like that. Maybe more than that. I don't really remember. And so that's enough to give it just a little bit more of a lurch for the side of the Earth which is closer to the Moon. And then there's the side which is opposite the Moon. And that's going to have the least effect, right? But there's this swelling that happens right here because the center and everything else, right, it's moving an average amount, right? The side that's closer, or that's closest to it, is moving the largest amount, and this side, it's kind of resisting it, right? And so there's these tidal forces that are kind of trying to string out the Earth. It's stretching it out, trying to spaghettiify it, or whatever. And so the Moon is, it's not large enough to rip the Earth apart for that, or whatever. So that's no harm done, right? And in fact, it seems to have a great benefit in that it may contribute to keeping the Earth's core active, and in which in turn would contribute to um, the cycle, is it the iron cycle or whatever, the subduction zones or whatever. So it's active. It spews out volcanoes whenever it hits the right angle and finds a vent that comes out to the surface, and then that kind of draws in things from the bottom of the ocean. It draws in whatever sediment has made its way down there, and so it sort of cycles through it. All right, so yeah, hooray moon, right? Okay, but this action, right, where you have this gravitational body that's pulling on it and it stretches it out, those are called tidal forces. So now let's go back to the photon. Okay, so you have this wave, and it's surrounded on all sides, really, by gravitational objects. And so every one of them is going to apply like some net effect or whatever on it. But the net result is that over time, that photon is going to be stretched. Whenever it passes by a large object, then it'll experience basically the same tidal forces that we were just describing in the Earth, where this one gets stretched out a little bit more, and this one, an average amount, and this one a little bit less. But the net result is this loss in energy. But in doing so, as it loses that energy, as the photon goes from some high energy photon to some lower energy photon, as its frequency gets reduced, it does so as a result from participating in gravity, and so it was the muscle fiber that was holding together a region of space over some period of time, and so the energy lost, the electromagnetic energy lost from the photon is going to be realized as work done while acting as gravity. So it's gravitational work done by the photon, and so again we get this cycle, right, where all this energy comes together, it fuses, it creates this light, or whatever, the light goes off into the distance, and then it feeds its energy back into keeping everything together enough that that we have galaxies and so forth. And so this trade-off, is explained by the new model, right? And what's really satisfying is that so that the energy of the photon will be described by Planck's equation. So Planck's constant times the frequency of the light. And so as this frequency diminishes as a result of tidal forces acting on the photon, so that decreases. But the mass energy of the system is compensated, so it feeds from here into there, and so that is I believe that to be the arithmetic error that brought about dark energy and dark matter. So it's this fairly simple concept. But the great news about that is that this kind of opens the door for exploration into this new model. And so okay, so that's the role that conjecture plays, right? So you just come up with this idea and you start. The idea is that you're allowed to speculate. You're allowed to just guess and be wrong, or follow a thread until it leads to a dead end. And either and the great hope is that as you're following that thread, either it will lead somewhere productive, or even in failure, that it will lead somewhere productive, that you gain some better understanding about the models that already exist, or some way to reinforce something that is already well described, and so you're at least gaining understanding, even if you're not making some new breakthrough. Okay, so we spent all that time talking about coverings, and the coverings would be important if you're trying to codify this, right? So if you want to write a program that can represent or simulate actions at the subatomic level using behaviors described by this model, then you would go back to the covering, and the covering would be the way that you describe those regions of space, and that you can divide up however much space you're looking at and you're simulating. So you can divide it up, and you're not repeating any actions, and that properties like the conservation of energy are preserved, and what I believe to be equal to the conservation of energy and the conservation of charge would be the conservation of surface area of this four-dimensional structure. And so basically that it's like a pug dog's face. The skin is already there, you're just moving it around, but the amount of skin that's on the surface of that dog's face is always the same. And so I that's how I envision it in my mind, is that there's just these wrinkles on the surface of this four-dimensional sphere, and they're moving around, but it would never be smooth, right? It's always going to have, there may be some minimum amount of wrinkles that it would always have, but the amount of surface area, there's just more surface area than necessary in order to cover whatever's going on the interior of the sphere. And so you end up with these wrinkles, and those wrinkles are conserved. Anyway, so I'm not sure if we'll continue this discussion on Thursday, if we'll play around with trying to code it, or if there's something else that that would be more fun to go over. So I'll think about it. We'll figure it out on Thursday. All right. Good luck with the exam, and I'll talk to you then.